Unit 15 is called Integrals of Transcendental Functions. And transcendental just means that they're not polynomials, so these are all kind of the special cases. And we're going to start with lesson 15.1, finding integrals of exponentials. So when we say definite integral, we're actually finding the area under a curve between certain x values, or the lower and upper bounds. And so the rules are that if I'm trying to antiderive or integrate the area under the e to the x function, it is itself. And that reminds me, because when we find the derivative of e to the x, remember it was always just e to the x. So that makes sense that either way it is itself. The only thing that's going to get different is when we have like this chain rule where the power has a number times x. But think about if I were taking the regular derivative of e to the, let's say, 2x. Remember that it was itself, e to the 2x, times the derivative of the power, which was times 2. So antiderivative is going to do the opposite of that. So instead of multiplying by 2, we need to divide by 2, or actually multiply by the reciprocal of 1/2. So what you see here is instead of multiplying by n, we're actually dividing by n, or times the reciprocal of 1 over n. So it's pretty simple to see the connection. Let's try one. We're trying to find the area of this function from 0 to 10, and we'll express our answer in simplest form. First of all, I might want to change this point 2x to, you would read that as 2/10, because it's in the 10th spot, which reduces to 1/5. So I'm going to change this to 6e to the 1/5 x. You wouldn't have to do that, but it's going to help me. Okay, so I'm trying to anti-differentiate that. So again, it's going to be itself, 6e to the 1/5 x, but then I need to divide by 1/5, which is the same thing as multiplying by the reciprocal of 5. And then any constant that does not have a variable gets an x tagged on the end. And you could always think, well, I'm going to anti-derive, or I'm going to differentiate this to think, what's the derivative of 2x? Well, that would just be 2. And we're going to find this area from 0 to 10. Okay, so then that would really be 30 e to the 1/5 x plus 2x. I'm going to plug in 10 first, because this is my b and this is my a. So it's 30 times e to the 1/5 of 10 plus 2 times 10 minus, and I'm going to do brackets around it, plug in 0. So it's 30 times e to the 1/5 of 0 plus 2 times 0. 1/5 of 10, or 10 divided by 5, that's 2. So I get 30e squared plus 20 minus, don't count this all 0. 1/5 of 0 is 0. But having e to the 0 power, anything to the 0 power is actually 1. So we're taking 30 times 1 is 30, so it'd be minus 30. 2 times 0 is 0. So to simplify, just combine my like terms, and I get 30e squared minus 10. And that's all I can do because e is an irrational number. Remember, it's about 2.7 something. All right, let's try one more. It's very similar. Only difference is the power is negative. So we've got negative 0.5x, which you know is negative 1/2. So to integrate, we're going to have itself. But then I need to divide by negative 1/2, which is the same thing as multiplying by negative 2. And then I need to add 1 to the power. So that would be x squared, and then divide 8 by 2, which is 4. And you could always check with the power rule, that's 8. That would be x. I want that between 0 and 2. So I would get negative 2e to the negative 1/2 times 2 minus 4 times 2 squared minus, now plug in 0, negative 2e to the negative 1/2 times 0 minus 4 times 0 squared. Negative 1/2 of 2 would be negative 1. So I get negative 2e to the negative first. 2 squared is 4 times negative 4 is negative 16. And then I get negative 1/2 of 0 is 0. E to the 0 power is 1. Negative 2 times 1 is negative 2. Minus a negative 2 would turn into plus 2. And then that is 0. I'm going to fix this negative power by sinking it to the denominator. So it's really to the positive first power, and then combining my like terms, which would be negative 14. So it's negative 2 divided by e minus 14 would give us an actual number of the area under that curve.